All right, welcome. We are about to dive into the invisible forces that pretty much shape our entire universe. We're going to go from the tiny spark of static electricity all the way to the fiery heart of a star. Let's get into it.
So, what do you think? It sounds like a riddle, doesn't it? A flash of lightning, that beautiful light show in the sky, and a totally revolutionary power source. Well, the answer to all of it is a kind of cosmic dance between electric charge, a supercharged state of matter, and the invisible lines of magnetic fields.
You know, to really understand this dance, we have to start with the basic steps. And that means going right back to the fundamental force that tells charged particles how to behave, especially when they're just sitting still.
Yeah, we're talking about electrostatics. This is the world of static cling, when your sock sticks to your shirt or that little zap you get from a doorknob. But we're going to scale that idea up to a cosmic level. And it all really boils down to one simple, elegant rule.
This right here, this is the rule book for how charged particles interact. And it's simple. Opposites attract, likes repel. And the farther apart they get, the weaker that push or pull becomes. Seriously, this is the foundation for everything we're about to talk about.
And here's where it gets really interesting. Charges can actually influence each other without ever touching. It's a process called electrostatic induction. A neutral object can get pulled into the action. Its own internal charges start shifting around, all because of a nearby force. This idea of action at a distance, well, it's absolutely key.
So, that's what happens when charges are, relatively calm. But what happens when you pump so much energy into a system that you literally tear the electrons right off of their atoms? Well, you get something totally new.
You get plasma. It's often called the fourth state of matter, and it's not some rare, obscure thing. In fact, it's the most common state of matter in the entire universe. Our sun, most of the stars you see at night, they're just giant balls of plasma. You've even seen it here on Earth in something as simple as a neon sign.
And this comparison just lays it all out perfectly. A normal gas, it's neutral. It's not great at conducting electricity. But plasma, it's a totally different beast. It's this soup of free-roaming charged particles, which makes it an amazing electrical conductor. And that right there changes everything.
So this is the crucial part. Because plasma is just made of charged particles, it doesn't just conduct electricity, it actually creates its own magnetic fields and reacts really powerfully to other ones. And when it gets all excited, it releases that energy as light. That's the glow you see in the aurora, and it's the brilliant flash of a lightning bolt.
Okay, so let's scale this up. Since plasma creates magnetic fields, and the universe is just packed with plasma, that means the entire cosmos is crisscrossed by this invisible magnetic architecture.
This is the fundamental link right here. Anytime you have charges that are moving, you get a magnetic field. And plasma, by its very nature, is a massive sea of moving charges. So it's basically a natural engine for generating these enormous magnetic fields that stretch across entire galaxies.
But here's the twist. While we know that plasma is great at amplifying magnetic fields that are already there, scientists are still debating where the very first seed fields came from in the first place. It is a huge, profound mystery that drives a ton of research in astrophysics today.
So, now we've got our two dance partners on the floor. You've got plasma, the supercharged matter, and magnetic fields, the invisible guiding force. And when they finally come together, believe me, the results are nothing short of spectacular.
This beads on a wire analogy is just perfect. The magnetic field is like an invisible wire, and the charged particles in the plasma, they can't just cross it. They get trapped, forced to spiral along its path. It's how you can channel these immense amounts of matter and energy through space.
And that level of control leads to some of the most powerful, most mind-blowing events in the entire universe. The violent eruptions on our sun, these colossal jets of matter shooting out from galaxies, the swirling disks of doom around black holes, all of it is governed by this cosmic dance.
Now, the engine behind a lot of these explosions is something called magnetic reconnection. Imagine magnetic field lines are like giant cosmic rubber bands. When they get twisted and stretched too far, they snap. And when they snap, they explosively release all that stored energy. That release is what powers something like a solar flare.
Okay, so for the final act, we've seen this incredible, awesome power out in the cosmos. But what if we could control it? What if we could bring that cosmic dance right down here to Earth and actually harness its energy?
And that is the whole goal of magnetic confinement fusion. It is literally an attempt to build a miniature star inside a laboratory. We're trying to use the exact same magnetic field principles to trap plasma heat it to millions of degrees, and force atoms to fuse together, which releases clean, nearly limitless energy.
But, as you can probably imagine, containing something that's hotter than the sun is, well, it's not easy. Plasma is notoriously slippery stuff. Those beads on a wire have to be held in a perfect magnetic bottle, often in these incredibly complex, twisted shapes, all designed just to keep those superheated particles from getting out.
So just how strong do those magnetic fields need to be? Get a load of this number, 20 Tesla. To put that into perspective for you, that is monstrously powerful. We're talking about 400,000 times stronger than the Earth's entire magnetic field. That is the kind of raw power it takes to control this dance and build a star right here on Earth.
And that brings us to our final thought. For thousands of years, we've just been spectators, watching this cosmic dance of charge and energy from a distance. But now, we are on the verge of not just understanding it, but maybe, for the very first time, actually learning how to lead it. And you have to wonder, what's that going to mean for our future?